Wait.
My soul.
Everybody's
Am I right?
Your soul.
Am I right? Or am I totally right?
It changes course after an hour.
Have you guys figured out the picture, like how it makes sense from the words?
No.
Okay, where did the ship start from? Good.
I thought it was a plane.
Well, it's a little, yeah, it kind of helps to see how he's pointed, but he started A. Now, what does the wording say? The ship leaves port, so here's port at noon and heads due
West.
Okay, well, it's headed due west, right? Thinking about my compass. It's headed due west, straight west. Due west at 20 knots or 20 nautical miles per hour. At 2 p.m. Question, how long has it been going for?
2 hours.
Okay, so how many miles did it go if it's going 20 miles per hour and it's gone 2 hours?
40
Exactly. Multiply the speed, rate times time, the speed times the time. And if you want to think about just building a bridge, couldn't you build the bridge too? 20 nautical miles per hour times 2 hours. Don't you get 40 miles? So you could think dimensional analysis, or you could think of distance equals rate times time. Either way. That's what I labeled that with 40 nautical miles. Okay, now what happens at 2?
Changing course.
Okay, so at B, it's changing course. Does it make sense how the angle that it's turned is north 54 degrees west? What does that mean? Start from north. Start with the first one. So from B, where's north of B? Straight up. You would do the compass straight up from B. That's north, and it turned what degree? Towards the west? Does that make sense? So, north, 54 degrees west. Okay, now it starts heading this direction, as shown below. Find the ship's bearing and distance from the port of departure at 3 p.m. Okay, how much time has passed? An hour. Did it say that it changed speeds at all? No. So then, how far has it gone in this direction? 1 hour times 20 nautical miles per hour would be 20 nautical miles. Okay, does the picture make sense?
Yes.
What are they asking for though? Bearing, that's like some sort of angle, and distance from where?
60 knots.
Okay, so the distance, isn't that another way of saying it? Couldn't we say find C, right? Because wouldn't little c be how far, if it needed to return to port right now, got an emergency call, something, someone forgot their iPhone, I'm just kidding. That's not an emergency. Go back, right? How far would they have to go? That's C. Okay, now question. Bearing? Is it bearing from the ship to the port, or bearing from the port to the ship? And the reason why I'm asking is, this guy's north, in a sense, is different than that guy's north, right? So whose bearing are we doing it? The ship, is he returning back, or is someone from port coming out to meet?
From the port.
Okay, so we have to come back to A and say, all right. So from this guy's north, what angle west? Does that make sense? I want to fill in from port. I wouldn't do south, because why would they start south and then turn? It doesn't make sense. North, west. The ship is northwest of the port, right? So I want to say, well, there's north, there's west. Okay, what angle from the port, what angle would they have to start heading on? What bearing would they have to find their bearing? What bearing would they have to start heading on in order to get there? Line to find us theta. But the problem is, man, is that theta even a part of this triangle? So what am I going to find? Let's find that guy and subtract from 90. True? If I find this guy and subtract from 90, won't I get that guy? So I want north, what angle west, just for this guy to be able to know what direction to start heading. But okay, if I can find this alpha and then do 90 minus, I'll get the beta. Now hold on. What triangle are we trying to solve? Can you guys see that? If we were in chapter 6, we could do law of cosines, and we could use this triangle right here with no right angle. idea, since we're not in chapter 6 and we haven't done law of cosines, couldn't we make a right triangle and
Yes.
solve that? So once again, we could do law of cosines, you guys remember that from last year? C squared equals a squared plus b squared minus 2ab cosine of c. No? How about sine of a over a equals sine of b over b over equals sine of c over c? Law of sines?
Yeah.
Anyway, those are for non-right triangles, which, oh well, whatever, we have a right triangle. Whew, we get to skip the other. So what can we label to solve this triangle? Any ideas? In what corner? Okay, left bottom. Well, that's 90. Okay, that's good. What's this guy? Can't we tell who that guy is?
36.
Good, 36, so we can subtract from 90. Bummer, we don't got a lot. If I have a hypotenuse and an angle, and I need an opposite and an adjacent, can I find them if I need it? Aha! Using what? How am I going to solve for this guy? He's adjacent. Cosine.
Cosine.
Can't I say that D is equal to, see if you can follow, hypotenuse times cosine of 36?
Yeah.
Adjacent over hypotenuse is cosine. Move the hypotenuse over. Oh, sweet. Now I know D. Dun, 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 dun. How about B? Okay. Cosine, I know, it's Monday after Thanksgiving break, is adjacent over hypotenuse, and I solve for D. Are we tracking now?
Wait, where we go back?
Some people got stuck.
Oh.
Question, what am I going to use for B? Opposite. And hypotenuse, I'm going to use
Sine.
sine. Sine of 30. Good job, both of you. B over, can't I solve for B?
Yeah.
So isn't B going to equal 20 sine of 36? You guys agree? Let's move 20 to the other side.
That's 11.7.
Nice. I'm just going to type it all on my calculator though and not have to worry about rounding because rounding produces error. How am I going to use this to solve for C? C is a side. C is a hypotenuse. And I have one leg if I add and the other leg, don't I? So can't I say that C is equal to, can you guys fill in? Can anybody help me out? Square root of what? Tell me the math without doing any like in your calculator rounding, just from what's here. What would I do? 40, Patricia go, 40? All squared, right? Pause, are you tracking?
Yeah.
Okay, pause. Pythagorean theorem says leg squared plus leg squared is hypotenuse squared, right? Who's your hypotenuse?
Oh.
C. So I square rooted, C squared equals, and C equals the square root of A squared 40 plus 20 cosine 36. A squared plus B squared 20 sine 36. So C squared equals A squared plus B squared. C is equal to. And who's A? And who's B? So I took B, plugged them in. I took A, which was the addition of that guy plus that guy, plugged in. Yeah? Okay, what mode had you better be in? Yeah, if you're in radians, it's going to be just a whole lot of sadness. But guys, can't you just throw this whole thing in and not have to do 1,012 different? Just be careful with parentheses. Make sure you have the entire 40 plus 20 cosine 36 in parentheses before you square. And then go ahead and make sure the 20 sine of 36 is all in parentheses, I'm not kidding, before you square. I think C is equal to 57.397?
Yep.
Yeah? And that way there's no error. 57. Wait, not feet, not inches, not even miles, what is it? Nautical miles. But That distance isn't gonna mean much unless we can get the guy on the right bearing, otherwise he'll still end up in the wrong spot. So you gotta get him the right bearing in order to go out and move the shed. So question, how do I find the bearing? Don't go straight for theta, go for Lou first. Alpha. How do I find alpha?
Which sine of alpha is equal to 36 over 57.
Okay, is Andrew's process right? Is he taking sine opposite over hypotenuse and saying, let's go? Sine inverse? Could that work? Is sine opposite over hypotenuse? Yeah. Have we found the hypotenuse? Yeah. Does sine inverse let us get back to an angle from sides? Yeah. So would his way kind of work? Yeah. What else could have kind of worked? Cosine inverse could have taken all of that over that. But question, why am I going to say right now that neither of those are best? Why not sine inverse or cosine inverse? If it makes sense mathematically, take the opposite, take the hypotenuse, take the adjacent, take the hypotenuse. Why am I saying that's not necessarily best? What did we just do? Compared to what my calculator shows? We rounded. So if we take a rounded answer and plug in, what are we compounding?
Angle.
Error. Does that make sense? So if we plug in this guy, we're going to compound error. Now somebody goes, well, I'm going to plug in that guy. Okay, well, that's cool. Some people wouldn't have. What technically would be most exact? Using this at all? What would be most exact? Use what they gave us. And if we use what they gave us without any rounding, then technically, what trig function are we going to use? Tangent inverse. We're going to do opposite and adjacent because that's what we had from the beginning, no rounding error. Now, question, because of how many decimal places your calculator gets, as long as you use the 57.397100089, are you going to have an answer after we round the answer that's the exact same? Yes. So I'm trying to get the idea across that the exact answer would use the opposite and adjacent, not the rounded version that we just found. Does that make sense? So just for sake of argument, I'm going to go ahead and, if you guys want it, use the nice extended decimal in your calculators, you may. And to be honest, some of you using 57.397 with sine inverse or cosine inverse, that might work also. But I'm going to go ahead and say alpha is equal to tangent inverse of opposite 20 sine 36 over adjacent, which would be 40 plus 20 cosine 36. And technically, I'm not even going to solve for that. I'm just going to say theta equals 90 minus alpha. And I'm going to do that all in my calculator all at once. 90 minus second tangent inverse of little baby cool looking fraction, 20 sine of 36 all over 40 plus 20 cosine of 36. If you guys did use the rounded one, just trying to be daring and see if it will equal the same thing. For those of you that went the exact route as I, how does 78.181 look? After the 90 minus. After the 90 minus.
Yes.
Matching up, I've seen a few head nods.
Yes.
So I think, what would the bearing be? How would I write this out? North, 78.181 degrees. Now technically, if you guys remember some stuff from the past, do you think they might actually go to degrees, minutes, seconds because it's navigation? Oh, but we're in our calculators. Whew! Where did we find degrees, minutes, seconds in our calculators? Second?
Math?
It's a menu.
Buttons.
Apps, there you go. Yeah, we're going to the angle one, which is the second apps. Good, good, good. Do you guys see number 4, the little triangle with DMS, which stands for go to degrees, minutes, seconds? Pause and show someone in your group that does not have their calculator. Pause and show them. second apps, little triangle DMS, hit the DMS, and it's gonna take what you have and make it degrees, minutes, seconds if you need them. Yeah? If you need them, without having to do the whole dimensional analysis. So we could also say this is the same thing as north, 78 degrees, 10 minutes, 53.091 seconds west. Whew. All right, what was our?
This is wrong answer.
Okay. What was hard? Melanie?
I just have a question about it. How can we use inverse of tan?
Because I had to get to the angle. So remember when I write like normal cosine, normal sine, that's great if I know the angle. But if I don't know the angle, which would look something like, can I just do another example? Tangent of theta equals, let's say it was like 3/4, just without writing all the yucky stuff. What if I need to get to the angle? I have to use tangent inverse. Because only tangent inverse gets rid of tangent and gets what I want it to be. But what I do to one side, so remember, inverse trig says, give me the ratio, give me the opposite over adjacent. Tangent inverse says, give me the opposite over adjacent, I'll give you the angle. So that's what I had to do to get to alpha. Good. Any other questions where you're like in your process, you got left behind?
It's like finding the sides of like A and B. I'm confused.
Oh, for these little pieces? I went really fast. Basically, I had to zero in on this little triangle and think about what did I have, and at the moment, all I had was hypotenuse and angle. So to get opposite, I had to use a sine function and say, uh-oh, I need to solve for the opposite. So I set up my little ratio and multiplied to 20. To find the adjacent, I had to set up a little cosine ratio, which is down below. Still using my hypotenuse and my angle that I was able to solve for. And then once I had the little baby triangle, then I looked at the big whole picture and say, okay, for this entire triangle, the adjacent would be this 40, which was found from the 20 nautical miles per hour, times 2 hours. I had to take that 40 and add that additional 20 cosine 36. And then the opposite was just the 20 sine. And the whole reason Kevin and I didn't get the numbers was because I wanted to just plug it in all at once. It was simpler, but it does make it look funny. Gotcha now.
When I typed in the square root of like 40 plus 20 cosine 36,
Yeah.
mine was like a couple numbers off. I got 58.
Oh, let's see. Maybe this had something to do with your parentheses. Anything else that you guys got stuck on? That's good. Oh. Can you type cosine instead of sine on that one? And which cosine and sine will be close because they're both like less than 1 and then your decimal, so it'll make it look a lot closer than it really was. Okay. Anything else? Yeah. We're just getting going. Okay, zoom. Zoom.
Help me go fast.
Zoom.
Come on.
Is that commercial not being anymore?
I hate that.
The little kid like zoom.
Why are you so full of rage, Ryan? I'm not so like dumb sounds like
Whoa. We're back on the recording of us.
I understand, some people get annoyed by commercials. Here we go. Simple harmonic motion, another application. I'm gonna come back to Eileen and make sure that we're good on what she's working on, but simple harmonic motion, maybe skip me a line, everyone. But long story short, a lot of this is review, it's just applied a lot. Well, we talked about waves. So basically we're just saying, hey, that whole wave idea and how we said it can occur in nature in lots of different ways with oscillatings or with actual waves like in the water or vibrations or rotating. We're just saying, hey, let's actually use that idea now to solve something practical. But let me give you a second to get some of the terminology down. Just So if you don't have time, I can. Thanks, man. So that whole idea, waves are everywhere. Sound waves, light waves, electricity, water. But if you then say vibrations, also if you think about vibrations moving back and forth, and if you were to make it horizontal, so like springs, pendulums, anything that moves in some sort of cyclic manner, cyclic cycle, cycling over and over, periodic motion. Simple harmonic motion, which is one type of motion, there are others, but simple harmonic motion, a way of describing it would be a sine, what's that Greek letter again? W? Omega. A sine of omega t or a cosine of omega t. This is an application of the trig, the sinusoidal curves that we've been talking about. This is actually applied to motion. So, we already know period is time to complete one cycle, but looking at this new way, like if you were to come across this in physics, for instance, or in physical science. Question, how would you be able to take what you know about the period of sine and cosine and apply it to this one? What would be the formula to find the period to complete one cycle of any of these motions?
A.
No?
T.
No? Keep thinking. T is like X, if that helps.
I mind if I don't.
1 over t times
Not
2
pi, because it's sine or cosine,
1 over
but Joseph was close. What's the normal period of sine or cosine?
I said
1
2 pi.
over.
Oh, I didn't hear you, sorry, 2 pi, good. 2 pi over, and then instead of saying W, just say omega. So you can say 1 over omega times 2 pi, or, sorry, I misheard you. 2 pi, good. 2 pi over omega will be the period. That's just using what we know. We called it B because we were using like standard math variables, A, B, C, D, but they give us this equation, whatever, it's still a horizontal dilation. We can do that. Amplitude, that was easy. It's still, yeah, they called it A, no big deal. How high, how low from equilibrium, right? Frequency, do you remember how to do that one? Yeah, good. 1 over,
Period.
I heard it from a couple of you guys, 1 over the period. Remember the period, the time to complete one whole cycle, how far you have to go for one full cycle. Frequency says, okay, if you only have 1 unit of time, just 1 second or 1 minute or 1 hour, how much of your cycle have you completed? So you take the reciprocal of period and say, okay, for 1 unit of time, what we have gotten. So guys, the formulas aren't really new, it's just this whole omega thing, and then them saying, hey, you can actually get practical with it. So let's get practical with it. Ooh! Write an equation for the simple harmonic motion of the ball on a spring described in, well, whatever, the picture below. Where the period is, hey, they gave us a clue. What is the frequency? Oh, stink. So we need 2 things, right? An equation and a frequency. Well, the frequency is kind of easy, isn't it? Didn't he already give us period? Okay. So we can do the frequency pretty fast. We'll do that in a second, but how could we model the simple harmonic motion of the ball described? Where does the ball start? Yeah, it starts at 0. This is equilibrium. Think about, remember how we wrote our handwriting lines for the sine and cosine waves? Okay, 0 would be like our sinusoidal axis, right? And the ball starts at 0. Question, where does it go next? Scientifically speaking, if you hold the ball at equilibrium and you let go and it's heavier, then the spring is able to keep
Go down.
at equilibrium. It's going to go down, and then what's going to happen? It's going to reach to the bottom of until the spring is able to compensate for its weight, and then it's going to bounce back up. Now this one says it's going to bounce all the way back up, which is a little weird, but we'll say it's in a vacuum, we'll say it's just going to keep on going. So question, we know that simple harmonic motion, did they call it D instead of Y, right? D is equal to, what's my sinusoidal axis is 0, what's my amplitude, what comes next? 10. Am I going to use a sine or cosine curve if the ball is starting?
Sine.
Yeah. Cosine starts at the extremes. Sine starts in the middle, right? So I have to use sine because it starts in the middle. But pause, is this a normal sine curve? If it's starting in the middle and then it's going down,
No.
and then it's coming back up?
Negative sign?
Yeah, it's gonna have to be a negative sign, because it's starting by going down and then coming back up. So I'm gonna have to make it negative 10 sine of, how am I gonna find my omega or my b from earlier?
1 over omega times 2 pi equals
Good.
4.
They gave me the period, and I have to work backwards. Or if you like it better, 2 pi over omega is equal to 4. I can multiply up the omega, divide the 4. There we go. That equation will model my motion. Starting at equilibrium, it's a sine going down, not up. Normal sine starts by going up, so it must be reflective, hence the negative. I took the period and worked backwards and figured out that my coefficient must have been pi over 2. And then, you guys already even said the frequency. What was the frequency? 1 over the period, which is just 1/4. So every 1 second, it will go 1/4 of its motion. Every 4 seconds, it'll complete its entire cycle. Which, does this show the entire cycle? What's missing? There's one part missing, one picture missing.
Returning to the middle.
It would return to the middle, and it would keep on going, 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 going until it finally settles, right? How are we doing?
I'm not done.
Oh, not done. Lo siento.
Why does it start off so warm and just switches to cold?
It's cold outside too.
That's not.
Because it stays warm longer than it should, and it stays cold longer than it should. So the temperature gauge, wherever it is a little bit off. And on Sundays, they have nursery in here, so they kind of fiddle with it, so it resets, and so.
They have nursery?
Pastor Carmichael, or I guess you might be able to call him Mr. Carmichael.
A lot of these things don't have it.
His church meets in the gym on Sundays, and nursery meets in my church. Because I go there, Mr. Deacon goes there. You go there. Mr. Richards, he's starting having class coming. He's a good reader. I'll read my professor.
Oh, really?
He's a cheat.
Yeah, Mr. Marcus.
All right, you ready?
Mr. Marcus gives you
Okay.
12-page packet.
Oh, it's Bible or no?
No, that was in Bible
Okay, I
last
was
year.
gonna say.
Battle last year, everybody in my class.
It's like you tell me, like,
Question!
cut out like half the packet.
Is there anything that you need to actually write down from this page?
Oh.
One illustration of the relationship between sine curves and harmonic motion is the wave motion that results from. Haven't we already talked about this?
Yeah.
What picture did we look at on my wall?
That one.
This one. And what did we see at the very beginning of sine cosine curves? It's a wave. Okay, so let's move on. Go team. Oh, this one.
That's just too much.
You guys see this one's 3-dimensional, not just 2-dimensional? Because the bobber is not just moving in one plane, it's also moving into other planes as well. But anyway, just shows you 3-dimensional. Just shows you it's not making you like do all this math. Just showing you how things get a little more complicated. Homework, section 4.8. Let me get up your homework page. Either you're writing down 4.8 homework because you're like, yeah, I was a slacker and I didn't start it. Or I was not a slacker, I was working on other things that were higher on my priority list.
Yes.
But some of you did work on it, and you need to write down the other homework. Wherever you are, get out your spirals. Either you're writing down the review, or 4.8, or both. The review, or 4.8, or both. And anybody who did start homework and got to anything tricky, let me know what it is now. Actually, no. Give me 30 seconds to actually get up your book first. Then you can tell me where you got stuck. And then all of a sudden it switched, right? Was it where bearing happened?
No, it happened halfway through the chapter.
Oh, through the chapter. I thought you meant the section. Sorry, Jonathan.
Which side or what?
That's where pre-cal stopped and had a a quest.
Wait, what is it supposed to be?
All right, you guys are writing down 4.8 and or the review. Maybe taking a picture of it. And anybody who worked on homework over the break, section 4.8 preferably, do we have any places that we got stuck? Doesn't like my file today. Yeah. 17? Okay, any other ones that got number 17 on 4.8? Any other ones that we want to look at? None of the word problems? You haven't gotten them? I'll get number 17's info up. It's actually an easy one to write down as far as what's been given. The goal is to find the altitude. If someone else has one, just shout it out. There's definitely some word problems in there. Yes, there's a picture for number 17. If you didn't see it, it would have been really hard.
You know I can do it.
Alright guys, number 17. Talk about the math talk through the math with me. It says find the altitude of an isosceles triangle. Isosceles triangle, the two opposite angles are congruent, which means what about the sides? Okay, so those two angles are congruent. These two sides are congruent. They want me to find what? It's not even in the picture. What's the altitude?
The middle.
The altitude is 8.
And the altitude of an isosceles always hits at a...
90. Perpendicular.
Good. It's always perpendicular to the base, hence it always hits at 90 degrees. So what can I do if I know beta is 32 and b is 8? Yeah, why, or how can I divide the 8 legally?
Tangent. 4 and 4.
Good. Because it's going to be a perpendicular bisector. Does that make sense?
Yeah.
Maybe that's a little geometry-ish, but if it's an isosceles triangle, the altitude is going to perpendicularly bisect the base. So I can say 4 and 4. Colby, why were you thinking tangent?
There's no hypotenuse.
Yeah, they didn't tell us anything about the hypotenuse. So I can plug in the opposite is A, and the adjacent is, can we solve?
Yes.
Yeah.
2 acids.
Okay, number 34, another question. It's a bit more of a word problem. Let's see if the book wasn't liking me a second ago, my file. Let's see if it opens now. Section 4.8. It doesn't like me. I don't know why. Oh, it likes that page. It likes that page. Oh, it doesn't like that page. Nope. Okay, never mind. I have it up here.
Dude, that just like, see, originally, when we break it, so it was moving in 2 weeks and finally we're done. And now this one's terrifying. We're going in 2 weeks. It's 3 more weeks. Oh, I forgot.
Hey guys, quick question. Always. Angle of ascent, what's that talking about? Take off, plane taking off, angle of ascent, angle of elevation, good. And I also said its speed, we talked about rates with the whole nautical miles per hour, right? 275 feet per second. So how can I draw the picture for this situation? Okay, draw a triangle. I have a plane taken off, right?
18 degrees.
18 degrees is what's going on here. And then, isn't this side ever expanding?
Yeah.
Because the plane just keeps on flying. It's not like stopped dead in the air. Okay, so when for letter A it says, find the altitude after,
10 seconds.
I think it's 1 minute,
60 seconds.
which would be 60 seconds. So how do I deal with that?
2 seconds.
Okay.
As the hypotenuse.
So you can think dimensional analysis. I know 275 feet per second, multiply it by 60 seconds, which is 1 minute. Well, I guess I don't need the 1 minute, do I? 60 seconds. Then I can end up with, wait a minute, what's that going to measure in my picture then?
Hypotenuse.
How far it's gone, right? So it's going to measure like this one, which if that's my altitude, I could, I don't know, name this one C, I suppose, right? So this would be my C after 1 minute, but that's not what they're asking me to find, is it?
Sine 18 equals, oh wait, you're right.
Yeah, you want sine, because you have opposite hypotenuse, right? So sine of 18,
Equals A over, what is that?
275 times 60? Yeah, we'll be lazy, that's okay. So then how do we solve for A?
Move it to the other side.
Uh-huh.
This is easier than I thought it was.
They all fit.
60,000
And that's the final?
No, that was
Okay, so multiply by sine of 18 in degree mode. But that's not, sadly, all of this question. B goes ahead and says, I think we have time for B. 5,098, so 098?
0.780.
Cool. Guys, what would the units be if this is the altitude?
Feet.
Good. Real quick, even though they told me 1 minute, it makes sense that we have to go to seconds because of our units, right? Let me make sure I wrote it down right. 50 feet per second, right. Letter B says, how long, and this is probably the harder part, how long will it take, Rebecca, do you have this part? Do you have the info on me? How long will it take for the plane to reach, I just don't know what the next part is. 10,000?
the one that says A equals 10,000 celsius.
Ooh. So what would the equation be if we didn't know C?
10,000 sine of 18 degrees equals C.
Good. I could say sine of 18 degrees. I know A this time, but instead of doing this whole 275 times 60, well, wait a minute. Hold on. We need the time. We need this part. So Andrew, pause. We're not just going to make this C. We're going to make this 275, because we need the time, not the length. 275 times what?
C. No?
Not C. We actually don't care about C. Times T. I need to know the 60-second part. I need to know the time part. So I'm keeping the 275. It's still going at that speed, but I'm changing the time, saying, well, I don't know how many seconds, and then I'll solve for T. All right, okay, so we're able to cover a couple questions and homework. Come tomorrow with any more you might have, but work on this because tomorrow we want to review. Bye, guys.
It'd be a lot easier.
Some people don't like numbers.
No, since they just moved out, they didn't say any words.
If you've never applied math, it'd be so much fun, but not practical. Oh, get a point.